Let's now talk about part 2 of implementing the Zippy microservice. And here we're going to take the features we developed in part 1 with the Zippy quote repository and the custom SQL query, and we're going to show how to implement the Zippy application, Zippy controller, and Zippy service classes. And this implementation will use both parallel and sequential versions or access points of the Jakarta Persistence API using parallel and sequential streams. So this implementation, of course, is available in the EX4 project in the WebMVC folder in my Live Lessons GitHub repository. So here we are back in the Zippy package, and now we're going to take a look at the Zippy application. And this Zippy application is quite interesting. I have extensive comments up here explaining what is going on with these annotations. You're welcome to read through them, but in a nutshell, this is a Spring Boot application. It's going to scan these components to find things it needs to be able to do various kinds of dependency injection and auto wiring and so on. It's going to scan this quote class, which we took a look at before. This is the one that has the annotations that make this an entity that can be used in the SQL database. We enable JPA repositories so that we can use this with the Java persistence architecture, the Jakarta Persistence API. And we tell it to go find that in the Zippy quote repository, which is right there. And then finally, we enable caching, which says do server-side caching of things we mark with annotations to be cached. You can see the Zippy application extends the base application, and it inherits this run method, which can be used to kind of start everything up. And that also has the side effect of creating a name for this particular microservice, the Zippy microservice, so it can be registered appropriately with the Eureka mechanism. We'll take a look at that in just a minute. Okay, so that is the application. Let's look at the controller. Controller is super duper simple because we pushed all the details into the base controller. So recall that the base controller defines all those get and post endpoint handler methods. And so our controller just extends that and then parameterizes the generic type T here in the base controller, which is up here, with the type that's used for the Zippy controller, which is going to return a list of quotes. And the other important thing it does is it auto wires the Zippy quote repository. So it knows how to make the constructor that initializes that particular field. Let's go take a look now at Zippy service. This is really the most interesting part of this. And Zippy service implements base service. If you recall, base service is, again, a generic interface that just defines the methods we have to fill in here. So we know what our obligations are. We're also going to parameterize that with list of quote, just like the controller did. We are auto-wired to our Zippy quote repository, which we took a look at in the previous part of this lesson. So now let's start getting into some of the interesting methods. So the first method is a very simple one. It's going to be get all quotes, but I did some fun stuff to it to make it more interesting. So the first thing you note I did is I made this method cacheable in the Zippy cache. And what cacheable means is that this enables server-side caching. And you'll see how this works when we actually run this program in a bit. And to make it clear why it works and that it's working, just for kicks, this is not what I would do in production code, just to make it work for the demo, I put a sleep of 4 seconds in here. So that anytime this method is called and it actually runs, it's going to sleep for 4 seconds. And so what you're going to see when we see the timing later is the first time this is called, it's going to sleep for 4 seconds and then return the results. And the second time it's called, it will not sleep for 4 seconds because it cached the results and it just returns the values from the cache, which is super duper cool. This is a good example of something that's worthwhile caching because it always returns the same results, at least for this implementation, the list of Zippy quotes. So we can put it in a cache and just return it without having to go and query the database each time. The first time in, however, we do in fact query the database, and this call will essentially go out and select all the rows in the table and return them. That is something that is automatically generated using the Spring JPA features. So that's get all quotes. And that does method level caching. Let's now go take a look at another method. This is called get quote, where we give it an integer. And in this case, we're going to also use client or server-side caching, except this time we're going to be caching based on the quote ID. So if you call this method with a given quote ID, the first time it runs, it'll sleep for 4 seconds. Again, not for production code, just for demoing. And then it will go ahead and use another automatically generated method that's part of the JPA repository called find by ID. So it's going to go look up in the database using the ID column, which is the primary key, to find the record, the quote that corresponds to that. And if it doesn't find it, it throws the illegal argument exception. But assuming it finds it, it then returns it as a quote. However, because we put cacheable up here, Spring now knows that it should cache the responses based on quote ID. So the next time we ask for quote ID 13 or 0 or 10 or whatever that is, it'll just return it from the cache rather than having to go do this query. So this is demonstrating a finer level of granularity of caching. Let's now go take a look at post quotes. Post quotes is a post request, and it passes in the list of quote IDs as the body of the HTTP post request. And you can see what it does here is it once again forwards the repository, this time calling the automatically generated find all by ID method, which, as it suggests, is going to take a look at the quote IDs and it will return a list of quotes that match those IDs. So far, so good. So, as you can see, most of what we've done here really has not involved any database programming whatsoever. We're just making calls to automatically generated methods. Now we finally get into something where we don't have an easy way of having one method in the database that does our bidding. Now, we could have done this by adding yet another custom SQL method to our multi-query repository and multi-query repository impl, but we didn't do it just so I could demonstrate what we could do instead. So down here, we're going to pass in a list of queries and a flag that indicates whether we want things to run in parallel or sequentially. And what this is going to do is it's going to use either Java sequential or parallel streams based on that parameter, and the Java persistence, the Jakarta Persistence API, the JPA, to locate all quotes whose ID matches the list of queries and return them as a list of quote objects. I think this should actually say all quotes whose quote, not ID, matches the list of queries and return them as a list of quote objects. Make sure I said that up here. Yeah. So how do we do this? We go ahead and use our stream support helper method, stream, to take the list of queries, turn them into a splitterator, and then run them either sequentially or in parallel. So this is now either a sequential or parallel stream. And then for each of the queries, we're going to go ahead and use the find by quote containing ignore case method, automatically generated by the underlying JPA repository, to go look and see if there's any matches that match that particular query in that stream of queries that we got here, either parallel or sequential. So it's going to go look up, and that's going to return a list of quotes that match that query, if any. We take that list, we turn that list into a stream, and then we use flat map in order to map all of those streams of quote rows in the database that may match the query into a stream of matches. And because of the way this is done, we have to eliminate duplicates because there may be duplicates in that stream, so we're going to get rid of them. And then we finally convert the stream back to a list. So this is how you can use automatically generated methods that are part of the Spring Data API support in conjunction with sequential or parallel streams in order to be able to get this aggregate feature where you can find any queries that match in the database. And again, we could write our own custom query to do this too, but we did it this way just for fun. Then the final example, which is called SearchEX for extended, is going to just make a single call to our custom query method, which was the part of the multi-query repository impl that will find everything that might match all of the queries. So this is an and, whereas this is basically an or. And you can see there that that's going to take advantage of the code that we wrote to do the query against the database. So that's essentially what's going on here from the Zippy service point of view. I do want to point out a couple of other things real quick. So if we take a look at the resources part of this program, you'll see that we have a Zippy folder. And the Zippy folder has a schema which says what the database table looks like. So we have a table called quote, uppercase, and that's going to have each element in here will have a big int, which is the quote ID, which gets automatically incremented as it's generated. It has a quote string, which is a string that is no more than 10,024 characters. Nothing's bigger than that. And we make the primary key be the ID, which is this guy up here, which is this big int. Here then is the data for that table. So we have the table, so we're going to insert all of these elements into the quote table with ID followed by quote, and you can see here what the table initialization looks like. So the default here just says auto increment the quote ID, and then we have all the Zippy the Pinhead quotes, which are silly and fun. They happen to be in alphabetical order. It doesn't really matter how we do it. We can always sort it if we need it for some reason. So that's how we initialize the database. And then finally over here, we're going to see some really fun stuff. So this is the application YAML file. And if you recall when we looked at this earlier, we used hard-coded port numbers for the Handy microservice. So this says listen at port 9100. And here's where to find the data for the Handy service. For Zippy, in contrast, we're going to say make the port be 0. And what that says is use the Eureka microservice to register Zippy with the microservice so that when the whole thing runs, it's going to know, it's going to tell the Eureka microservice, whatever port it happens to assign it, that microservice will then know that, Eureka will know that, and it can tell the gateway where to go find the Zippy microservice. So we don't have to hard code the port numbers. Some other things here that we need to do, you can see here that we say we want to use the Hibernate H2 database, and that's where we're going to store everything. And then this is telling it to go find the schema here in that file, and the data that initializes the data table, quote table here in that file. And then we also do some other stuff, basically saying what version of we want to use and some other things we need for debugging. So this is how you can configure your microservices declaratively using YAML. Handy is hard-coded to port 9100. Zippy uses the Eureka microservice instead. And I decided to make this kind of a hybrid example where Zippy is using Eureka, whereas Handy is not. And when we run this thing in a minute, we'll see how it all works. So that's the walkthrough of the Zippy microservice code. Also very important to look at this code because it will be something that you'll have to be aware of for your next programming assignment.